Welcome back to Math 104. We begin the second set of videos. As another example of an experiment that we can think about, just to illustrate that not all dice have 6 sides, let's consider 4-sided dice, such as the ones displayed here, where the possible outcomes are 1, 2, 3, or 4. Now, this might seem strange, the idea that you roll this 4-sided pyramid-shaped die, and it lands on a certain side, but which side is face up? There is no one side that's face up, so how do you know which outcome has occurred? Well, notice how the numbering goes here. Each corner here of each side has a number in it, and when a die lands, as this purple die has done, notice that 1 is on top here, 1 is on top on this side, and on the other side that's facing away from us here, there is also going to be a 1 at the top. So the outcome here, on this roll of the die, the purple die, is 1. The outcome on this die is 2, and the outcome on this die is 3. Now recall that last time we introduced the notion of an ideal data set for an experiment. This is a set of outcomes in which the relative frequency of each outcome equals its probability. For each outcome, what fraction it represents of all of the outcomes in the set is the same thing as its probability, its long-term relative frequency. If our 4-sided die is fair, then 1, 2, 3, 4 is an ideal data set. That is one occurrence of each outcome. Now, it's only because the die is fair that this is really an ideal data set, because in this set of results rolling 4 times, a quarter of all the outcomes here are 1. A quarter of the outcomes are 2, a quarter are 3, and a quarter are 4. That means that the relative frequency of each outcome equals 1/4, and that matches the probability, the theoretical probability of each outcome, which is also 1/4. So this set of 4 rolls of the die is already perfectly representative of what happens in the long run. So this set of 4 rolls of the die is already perfectly representative of what will happen in the long run. That's what makes this an ideal data set. But you could also write down this set, and it too would be an ideal data set of outcomes. There are 5 occurrences of each number. So here the 1s are a quarter of all the outcomes, so the relative frequency of 1 is a quarter, and the probability of rolling a 1 is a quarter. So relative frequency equals probability. Similarly for the 2s, a quarter of all the outcomes here are 2s. The relative frequency is a quarter, and that equals the probability. Similarly for the 3s, and similarly for the 4s. So this too is an ideal data set for the same experiment. Alright, where does that leave us? This illustrates that there are many possible ideal data sets for one experiment, but we still haven't talked about what these are good for and why we're studying them. Let's take the next step, which is, quite frankly, to start talking about money. Suppose you were using the 4-sided die to play a game, and for now we will continue to assume that this die is fair. In this game, whatever number appears on the die, 2 times that number is how many dollars you receive. So if you roll a 1, you receive $2. If you roll a 2, you receive $4. If you roll a 3, you receive $6, and if you roll a 4, you receive $8. This means that now, for each outcome, there is an associated payoff. That is, for each outcome, there is an associated dollar amount. Just as each outcome has a certain probability of occurring when you roll the die, so each dollar amount has a certain probability of occurring when you roll the die. Now here is a crucial follow-up question. What is an ideal data set of payoffs? In other words, what is an ideal data set of the dollar amounts? Not of the outcomes, but of the dollar amounts. Think for a moment what the answer should be. This is simply $2, $4, $6, $8. Within this set of dollar amounts, within this set of possible payoffs for the experiment of playing the game, each dollar amount has a certain relative frequency. In each case, that relative frequency is 1/4. And that relative frequency does indeed equal the probability of that payoff occurring. If you played many times, maybe you would be lucky and get some extra $8 payoffs. Or maybe you would be unlucky and get stuck with many $2 payoffs. But in the long run, the relative frequency with which each of these dollar payoffs occurs should be 1/4 of the time. That is to say that this set of outcomes is perfectly representative of what tends to occur in the long run. Having said this, what can we do with it? Before going on to the next video, answer the following question. In the long run, what will be your average payoff per play of the game?